authors Viet and Niels Henze, and it's about how to estimate the finger orientation from the capacitive screen using neural networks. And I think everybody of you have already used today a simple touch screen, and it's basically limited to X and Y coordinates, so the position of the finger. So in the last year, Apple came up with this idea of using force as an additional input, and I think many researchers already tried to establish other dimensions to enlarge the input on touchscreens. And this work is using the finger orientation, and here Wang et al. Already back in 2009, they used a tabletop with a back protection and a camera to estimate the finger orientation to overcome the distance between the finger and the target. And then later in 2013, Kratze et al. Came up with the idea of using a depth camera in order to estimate the finger's orientation. And here they mounted the depth camera onto a tablet, which that was the first portable version of an enhanced interaction for the touchscreen, so with the ability to use the pitch and yaw of the finger. And then 2 years ago in Madeira, Xiao et al. Presented their first idea of using the raw capacitive value of the touch sensor to estimate the finger's pitch and yaw, and they used Gaussian processes, and I will later describe why we think this is the first step and we can extend this work. So what we did in the first step in our paper, we collected ground truth data where we hacked Nexus 5 as Xiao et al. Did to get the actual capacitive data values from the phone, and we equipped the surroundings with a motion tracking system, as we saw in the last presentation, to track the finger's orientation as ground truth values for our learning model. So in our study, we asked participants to explore the range between a very flat finger and a steep finger, so 90 degrees, and from all the way to the left and the right, so from minus 90 to 90 degrees, so they explored this full space with their right hand. And during the exploration in the study, the experimenter was able to observe which areas already have been explored, and then the experimenter could hint the participant that there was an underexplored area, so to that the participant please explore this area as well, so that we capture all the whole volume of this the pitch and yaw to have good ground truth values for our machine learning model. And we conducted a study with 33 participants and with an age range from 20 to 33. And what we then did, so these on the right side, you can see a simple touch, what we get from the capacitive values. Here's the index finger touching the surface, highlighted here in yellow. And as you also can see, there is some filtering we need to do to really get that one blob of the finger. So we first did outlier detection. So sometimes the capacitive values are not perfect, so we have some peaks and we got rid of them. And then we did a simple blob detection that we ensured that there was a finger on the surface, because in the study, participants every once in a while just lifted their finger. So and then after filtering and the blob detection, we ended up with like roughly 500,000 sampled labels, so where we have the capacitive data values and the pitch and yaw of the finger. And then in the following slides, I'm going to show you what we did with machine learning, and this is the machine learning part is done with TensorFlow, and to ensure the quality of the models, we used 26 participants for training and 7 participants for testing. So there were no mix between the test and the training sets. Going back to what's out there, so what Xiao et al. Did, they used this capacitive matrix, and then they extracted in the paper 42 features, which they then feed into Gaussian processes models to estimate the finger's pitch and yaw. And Gaussian processes here have one limitation. The space required for training is an O of n squared, which for our data set is not feasible and a decent machine. And so that was one problem I'm going to show, and how we tackle this problem in the next slide. And our new approach is what we did. We just machine learning, and furthermore, we not extracted features here. We used the raw values from the capacitive matrix and piped them in and as an input. And we had two baselines for representation learning. That we had a k-nearest neighbor approach and a random forest approach, where for both we trained for pitch and yaw. And then we used deep neural networks and convolutional neural networks, and we did some of them. For all the models I'm going to show you in the following slide, we used a grid search to estimate the best parameters and achieve those results. So, as I said, Gaussian processes have this problem of the quite big space they use for training, and therefore we basically did two implementations of the XR model. We first used the Gaussian processes models, but only with 1.4% of the data, which roughly fitted, or is roughly the amount that XR et al. Used in their paper. And then this worked out for our implementation. So we have this Gaussian processes re-implementation, and then additionally, to make use of the big data set which we recorded, we swapped out the Gaussian processes learning and used deep neural network here. So a 3-layer actually. And then we have our k-nearest neighbor model, the random forest. Then we have one deep neural network, and the first deep neural network, the DNN here, is actually two deep neural networks. One predicts pitch and one predicts yaw. And then in the later steps, we figured that it's also a good idea to train one model for pitch and yaw at the same time. So we trained a combined deep neural network with two output neurons for pitch and yaw. And the three CNN models at the bottom of the slide, they're all combined. They're all training pitch and yaw at the same time, as this worked out better for us. And then we tweaked the CNNs with L2 regularization and batch normalization. Yeah, these are the results, the overall results, root mean squares and absolute means and SDs. And what stands out here in comparison to the XR et al. Model is that we can reduce the pitch from, so the deep neural network worked better than the Gaussian processes for both pitch and yaw. And from there on, we see that the k-nearest neighbor and the random forest with the feature representation worked also better as the feature abstraction, which was used by XR et al. And then we had the DNN, which worked slightly better than the KNN, but not better than the random forest. And we went on with the combined neural network, which improved the DNN, and then we switched to CNN, which really got us a boost. And here we were better than the random forest, and then at the end, the CNN L2 worked out best for us, and it's 8.9% achievement against the pseudo implementation of XAO and in pitch, and 45.7 in yaw. So what we actually did, so our Boston model, that's what I'm going to present you now. We started with a momentum optimizer. It's basically, you can also achieve the same results we achieved with the momentum optimizer with the gradient descent, but with a way longer learning time. So you need way more POCs than with the momentum optimizer. And then we also, for the weights, we used Xavier initializer, which also get at the time boost here to, it's basically setting some good values, 4 weights. It's estimated weights that are fitting into the range where you want to end up. And then we used constant biases of 0.01. And for the training, we used exponential declining rate, the values 0.01 and 1. And as I said, the CNN with L2 regularization worked out best for us, so we applied the L2 regularization of 0.015. So these are the hyperparameters we used for our model, and the model structure itself. We used 3 convolutional neural network layers. After each layer, we used the pooling layer, and the filter size was always the same for the convolutional neural networks, and we applied the 32, 72, and 160 filters. And we achieved all those values by applying a grid search and really narrowing down from a wide variety to as this worked out the best for us. And at the end of our model, we applied fully connected layers with a soft plus activation function, and in the middle we had 2,000 neurons, and as I said, 2 output neurons at the end to estimate the pitch and the yaw. So looking at the results of the model, then how did we actually achieve those average values? When looking at pitch, we clearly see there's a problem from the degrees, so from a flat finger 0 to 10, and basically this is due to an underexplored area of the flat finger on the phone in our study. So we have 2 little samples here in that range, basically because it was really hard in the study to perform 0 degrees. But besides that, the first peak of from 1 to 10, from 0 to 10, across the values were quite stable. And then looking at the yaw results, we have almost the same, having some jitter around that, but overall we get a stable error rate. So to conclude, we achieved a 8.9% achievement or reduction in error for pitch, and 45.7 reduction in error in yaw over the XORed implementation by applying feature representation learning to a convolutional neural network with L2 regularization. And all the data we recorded, plus training and model and testing, they're all available on GitHub, and you can see the link here on the slide. And in the future steps, we plan to move that used or trained model to a phone and actually implemented it and use it into some use cases. And as we used TensorFlow, this is a rather easy step. So if you want to do that as well, you're encouraged to use the model from GitHub and just apply it to your phone. Thank you for your attention, and I'm happy to take your questions.
Hello. Thank you for going over all those different options between CNN, DNN, and all those. So I think that's a nice thing to look at. You did mention that the limitation of the previous work, which you have marked 41 there, in the training was the running time. I think you said was n squared. Is that what you said?
No,
for the training?
No, it's the space you need on your drive, basically in your RAM.
So what is the running time for your classification?
I don't know, since we haven't ported it into a phone.
All right, so it's just a model right now.
Yeah.
All right. Thank you for your work.
Sure. Thank you.
Antoine Viet, University of Glasgow. Thanks for your work. I have a question about the interaction paradigm you decided to model. It looks like it's maybe two-hand interaction and just one finger over the mobile phone.
Yeah.
I was wondering if you know what would happen if the user is using just one hand interaction and maybe the thumb instead of the index, and whether the model would either tell you that it might be like several fingers or give you an indication basically.
Yeah, so with a one-handed interaction, I guess it's only possible to use the thumb in a very limited way. So you can't really you may be able to have different pitches, but different yaws is very hard. So that's why we went with the two-handed interaction. If you want to go with a one-handed interaction and apply that model, I guess it wouldn't work that well, since the blob, so the shape of the thumb on the touchscreen is way different from the index finger which we used. Yeah, please.
Hello. Is the trained model only usable on the Nexus 5, or can we also use different phones, or do we have to retrain it for every phone?
The problem, I guess, is not using a different phone. It's more of actually getting those values from the phone. So I think that's more the problem. And then when scaling to the same size, I would say that would work. So if the pixels are the real world pixel size is the same, or you scale it to the same, I would say the model works. But it's more of the problem of getting those actual values. It's quite hard.
Could probably use transfer learning, I guess, if you have a different finger or different sizes, maybe. Any other questions?
Leila from Waterloo. I may have missed it. How did you create or obtain the data set to train your neural network?
Like from the phone? Or
Yes, yeah.
so you can make some kernel changes to the Nexus 5 and flash the phone, and then you can live stream the data from the kernel's phone into Android, and then you can save it. And there's a link in the paper where it's explained how to do that.
Okay,
It's a
thank
hack.
you.
Okay, no more questions? So let's thank our speaker again.